Hello everyone, and welcome to today's episode of our Discover Molecular Interactions webinar series. My name is Vivian. I am responsible for scientific communication at Bruker Biosensors, and I am happy to welcome you to today's episode. Each month, we explore a different molecular interaction and we discuss its challenges, and we also discuss ways of analyzing it. And today is a very special episode, actually, of this webinar series, because this is the first episode that is focused on SPR. As now the Bruker SPR team and the Dynamic Biosensors team have been merged, and we now cover all the different technologies from high throughput SPR all the way to kinetics on cells. So I'm very excited to welcome you to this first SPR focused episode. And today we will explore the importance of thermodynamics for the drug discovery process, and we will discuss how to perform a thermodynamic profiling using SPR. And I'm very happy to introduce our guest speaker of today, Cyrill Brunner. Hi, welcome, Cyrill.
A warm welcome from my side as well. Thank you.
Cyrill is a trained pharmacist and he obtained his PhD from ETH Zurich. And he's currently heading the SPR application lab in Verlanden in Switzerland. And I am very much looking forward to your talk. If you have any questions during the talk, please feel free to use the Q&A function in the Teams app, or if you can't see that, you can of course also use the normal chat function. Or you can also raise your hand later on after the talk in our Q&A session, and I can unmute you and we can just talk directly. So without further ado, I will hand over to you, Cyrill, and I'm looking forward to your talk.
Thank you, Vivian. Again, warm welcome from my side to this premiere of SPR data in that series. Today we'll be looking at something a bit more uncommon, but equally interesting, and that is thermodynamics. Why is it uncommon? Most SPR assays revolve around determination of affinity and kinetic constants, so K on, K off, Kd, and derived values out of that, such as selectivity, so the differences between proteins, or also in screening, then the confirmation of data that you've obtained with other techniques. What we look today here at thermodynamics is a special case because thermodynamics already includes one component in the classical kinetic assay, and you need to add just a little bit in order to get more. What does it already contain? Kd is directly connected to delta G, so the Gibbs free energy, meaning the overall energy resulting out of the interaction between two molecules, for instance, a protein and a small molecule. Since they're directly connected, mathematically speaking, via an equation that's easy to calculate, you get also then the question, and what composes delta G in itself? And the two pairs, or like the twin basically, forming delta G, that's enthalpy and entropy. Enthalpy, that's the heat, so to speak, in the interaction of two molecules. So when two molecules interact with each other, there is heat produced by it, for instance, by intermolecular forces such as H bonding or van der Waals interactions. Entropy is then the chaotic partner in this partnership. So it's basically the liberty in movement in the interaction of two molecules. Entropy is connected to several intra and intermolecular properties, such as configurations on the protein, conformational change, water displacement in the binding site, and so on. And finally, and this is then the interesting part coming from SPR, since you're looking at an interaction in real time, you don't only get access to the end result, you also can see the state in between, or what is also called in biochemistry, the transition state energies, so the activation energies coming out of it. This gives us specific insight in certain cases into the binding mode, or actually in differences in the binding mode between two different molecules. I first tell you a bit like why thermodynamics is actually relevant. Where can you use it? What does it give you in addition to other assays? Why don't we do everything with an IC50 or a KD alone? The first example, or the first two examples, go in the same direction. It's about potency. This is an analysis from Freire et al. On HIV protease inhibitors developed late 80s and in the 90s, where they showed that the first-in-class compound, indinavir, in comparison to the best-in-class compounds, which are here the four towards the left, at the right-hand side, have a completely different thermodynamic profile. So you start initially with a compound that is mostly driven by entropic contribution, so by basically the chaos in the system, whereas the last, so best-in-class compounds, those with the highest potency, and actually also those compounds which have been shown to be best suitable against mutant versions, are mostly driven by enthalpic contribution, so H bonding and similar elements. An identical example has been observed with statins. Statins are cholesterol-lowering drugs that are often taken. It has started originally with fluvastatin, the weakest of all of the statins, so you need the highest dose in order to achieve the same effect, has a purely entropically driven profile, versus rosuvastatin, the best-in-class compound, actually is mostly dominated by the enthalpic contribution to the overall binding. When we look at drug design also from a more early stage perspective, then we can also use thermodynamics in the rational drug design. A very good example is docking. Docking is a computational procedure where you on the computer try to press your molecule into the binding site of your protein. And in grading which conformation or which protein might be the best, you typically use enthalpy, assuming that entropy is automatically compensated by enthalpy. However, that assumption isn't always true, and therefore it might be very helpful to actually know in the beginning what is the individual component or influence of the enthalpic and the entropic contribution on the overall binding affinity and energy. Additionally, if you do structure-activity relationship, this goes then a bit more in the classical medicinal chemistry pathway. So when you do small modifications of your lead compound, as you see here in this example, and with small, I really mean basically atom by atom changes, so going from a methyl to an ethyl group and so on and so on, you want to understand how that influences the overall affinity. Obviously, that's something you can do classically with SPR, for instance, determine the KD, but you also want to understand a bit better whether some of these changes might affect another component. And you see here in this graphic a very good example where the overall delta G, so the KD overall, remains more or less the same independent of the modification. However, the contribution of the enthalpic and entropic element to the delta G changes. So there's a difference in basically which molecule or which atom you add to that specific site of your lead compound. And finally, also something for the biologics people, because thermodynamics doesn't always or only apply to small molecules. It's actually useful also with protein-protein interactions. It might be a bit more complicated since the proteins themselves are a bit larger. However, with certain protein classes, it can be done fairly easily. Here is an example with a nanobody, actually 2 nanobodies binding to EGF. The first nanobody, the one in blue, has a about 10 times better off rate than the nanobody 6, the one in red. And if you look now at this transition state map, so this is basically what you see here. You have the original state, so the 2 components separated. Then you have the transition state in between, so where a part of the binding is formed, not the complete. And finally, the final state, so the actual complex. And you see that these curves go up and down. So up means that in this case, energy needs to be put into the system to reach that state. And then energy again is dissipated once you reach the final state. This is classically the transition state. And when you compare now to compounds, to proteins, to nanobodies, as in this case with each other, you start to see differences. So for instance, in that case, you see that the enthalpic element in the transition state is smaller in order to get to the transition state for nanobody 1, but getting back from the complete complex to the transition state, this is massively higher than for the red one. Similarly, the entropic contribution for the blue one, so nanobody 1, is different than it is for the red one, where the entropic contribution doesn't really play into it at all. So the overall combination of enthalpic penalty and entropic penalty in order to reach a transition state can explain, when you compare 2 nanobodies with each other, or the 2 components with each other, whether one or the other might actually do a better job in the off rate or in the on rate or overall in the kinetics. A similar example was found also with small molecules. That's with the adrenergic receptor A2A. Here it was about 6 compounds that were tested, and actually run in molecular simulations, so MD simulations, where they saw that some of the compounds tend to bind a bit higher up in the transition state, so when they're in the transition state in the binding pocket, whereas those that had a different binding profile, different transition state profile, as you see for instance here, were binding a bit further down in the binding pocket. And this can have an impact on whether you decide to go further with one or the other compound. Now, what is the workflow for that? The classical workflow that you do in SPR is you either do a multi-cycle assay, so you measure 8 compounds simultaneously, for instance, 8 different concentration, one after another. You can obviously also do that simultaneously. So you inject of one compound simultaneously 8 concentration. We call that either the multi-injection cycle kinetics, which is the top example here, or the single injection cycle kinetics, which is the bottom version. This is what you standardly do, set temperature 25 degrees. In order to get now the thermodynamic components, all you need to do is repeat the same assay, but at different temperatures. So you measure at, for instance, 10 degrees, 15 degrees, 20, 25, 30, 35, 37, 40 degrees. And for each temperature, you determine K on, K off, and KD, and take this then into a linear analysis, which in case of delta S and delta H, so the overall reaction enthalpy and entropy, we do a so-called Van 't Hoff analysis. Whereas for the transition state, we do a so-called A-ring analysis. Let's start first with the Van 't Hoff analysis. The Van 't Hoff analysis is nothing else but a linear fit on a logarithmic scale. So you take KAQ, KD, basically your dissociation constant. In this case, it was the equilibrium constant. Plot that, so put that in the logarithmic, plot that against 1 over T, so 1 over the temperature in absolute scale, and get then from the linear fit a slope, which refers to delta H, so the enthalpy, and the intercept, which refers to delta S, the entropy. And you do exactly the same also with the kinetic rate constant, so K on and K off. Here, it's not ln K, so the dissociation constant. Actually, here you pick either the association or the dissociation rate. In this example, for instance, we pick Ka, so that would be the association constant, and have identically as in the Van 't Hoff analysis from the slope delta H, here with a different index because it's a transition state energy, and from the intercept delta S, again also with the additional index. This can then look, for instance, like in this example here. This is the interaction of a small molecule binding to a protein measured at different temperatures, here with a color gradient. So the bluer it gets, the colder it is, and the redder it is, the warmer. So you go here from 5 degrees to 40 degrees, and you see that with each temperature increase, your off rate changes. So it goes from slower to faster, whereas the on rate goes from slower to faster as well. And if you take now KD values from that, you get then eventually in the Van 't Hoff analysis out of the slope and the intercept according delta H and delta S. Since our instruments are turned or designed to give as much information as somehow possible, can be sometimes a bit overwhelming to deal with all that data. So you need to come up with a bit of a different visualization. The easiest way to look at such data is actually a quadrant analysis. So we have a XY scatter plot, basically, with delta H on the x-axis and T delta S, so the entropy times temperature, in order to give a bit more equal scales, on the y-axis. And we separate now this graph in 4 different quadrants. The first quadrant, here in green, is characterized by having a high enthalpy contribution over the entropic. So basically, if a compound shows a high enthalpy contribution but almost no entropic contribution, it will be here in this quadrant. Quadrant number 2, here in blue, is the one where you have both components adding to the overall delta G. Most of the compounds end up typically in that space. The third quadrant, also very frequently occupied, especially with early stage compounds. Here we have those where the enthalpy contribution is smaller than the entropic contribution. Can be massively less or can also just be a little bit less. But generally, those compounds are considered to be more entropically driven. And finally, that's then dead man's land. That's the quadrant where delta G would become positive. So basically no binding could be formed. Normally, you wouldn't find a compound populating that quadrant. Focusing now on how do you do that also on our instruments. You see here our two instruments, the SPR32 Pro and the SPR64. Both instruments come with a inbuilt multiplexing capacity, meaning both instruments have 8 flow channels, so you can measure simultaneously 8 compounds at a time. They have a different capacity on how many proteins you can immobilize. In case of the 32 Pro, it would be a maximum of 3 proteins. In case of the SPR64, you can immobilize up to 8 proteins and measure simultaneously against 8 compounds. So they have a different degree of multiplexing and obviously then throughput that comes in the end, but both can do simultaneously a lot of compounds against multiple proteins and thus give within a single experiment a lot more data knowledge. The workflow, and I show here an explicit example done on an SPR32 Pro. In this case, we measured against 3 proteins. Those 3 proteins were carbonic anhydrase 2, 12, and BSA as negative control. Why carbonic anhydrase 2 and 12? Both come out of the same family. They're very similar on the primary sequence as well as on the secondary sequence level. So there's a bit of a selectivity question there automatically included. And the goal here was to see whether we can describe certain selectivity elements based upon the thermodynamics. That's why we measured 8 compounds simultaneously in a multi-injection cycle kinetics way, so one concentration after another. We measured these 8 analytes that you see here. Those are all sulfonamides, so they all have the same binding mediating moiety, that being the sulfonamide here, and then different decorations which typically guide the selectivity in it. We have compounds like approved drugs such as acetazolamide. We have compounds in there which are more fragment-like, like CBS, for instance. Also compounds which tend to be selective towards one protein, for instance, EMAC is reported to be selective towards carbonic anhydrase 2 over other carbonic anhydrases. The proteins were immobilized by amine coupling such that they covalently stay on the sensor surface. Here are the immobilization densities. The whole runtime of that assay, so we measured 8 concentrations, 8 compounds against 3 proteins, and that also over 5 temperatures, so ranging from 15 degrees to 35 degrees, all in 18 hours. So within basically a day, you get a complete picture of your interaction. Let's start first with the data comparison of SPR and ITC, because we wanted to back up also our data with ITC data. So we measured the same set of compounds in ITC. That was done in the same buffer condition against carbonic anhydrase 2, so against one of the proteins, because this is a well-established protein, so it also is well reported in literature to be working with ITC, such that we compare on equal levels and not apples with peaches. So we see here on the level of delta G, so basically KD, we have a very good alignment between the data, so both technologies yield similar results. When we look now at delta H and delta S, so the enthalpic and entropic energies, then we also see that the two technologies align very well. Small differences once in a while, but in certain cases, they are like almost spot on identical between the two technologies. So we can really go on and say, okay, with SPR, we determine the same values as we would with ITC in that case. Now, the goal in the beginning was already to look at selectivity, to add this multiplexing element and understand better whether we measure multiple proteins at the same time, whether we get something more out of it. And actually we do. So we look now at this visualization, this quadrant analysis again, and see here now the values for carbonic anhydrase 2 and carbonic anhydrase 12. And you see in certain cases we have fairly similar values. So for instance, as we look here on top at a compound, that celecoxib, celecoxib has more or less a similar entropic contribution in the binding to both proteins. The enthalpic slightly changes. What's also interesting, I mentioned that before, this compound here is in the third quadrant. You might remember this third quadrant is characterized by having a massively higher entropic than enthalpic contribution. So this compound is mainly guided by the entropic element in its binding, and it does that both to carbonic anhydrase 2 and 12. Other compounds, and there's a smaller fraction of them here in the first quadrant, so enthalpically driven, they are also enthalpically driven in both proteins. If we look here, for instance, at dunsilamide, actually binding to carbonic anhydrase 2 is enthalpically driven as well, not as strong, however, if it binds in comparison to binding to carbonic anhydrase 12. So we already see there's a difference in the enthalpic contribution of that binding, whereas the entropic contribution remains the same. We're moving here only along the x-axis and not along the y-axis. Another example is here EMAC. EMAC binds stronger to carbonic anhydrase 2 than it does to carbonic anhydrase 12. So here is the value for 12, here is the value for 2. And that might actually be explained by having a higher enthalpic contribution to the binding in comparison, so in binding to carbonic anhydrase 2 in comparison to carbonic anhydrase 12. The entropic contribution remains the same for both. So we really see if there's a difference caused by selectively binding. In this case, it is caused by the enthalpic contribution. Another example that I highlighted here is U104. U104 binds to carbonic anhydrase 2 with almost no entropic contribution, whereas binding to carbonic anhydrase 12 is actually a combined effect of enthalpy and entropy. So there's a difference in the way the compound is interacting. An additional information that we got out of this assay, when we look here again at celecoxib, heavily entropically driven, typically these compounds might have an issue also in solubility. A matter of fact, that was also the case. At 1% DMSO in the buffer, 50 micromolar, celecoxib was starting to crash out relatively quickly. Whereas at 5% it was soluble. CBS, this is the compound that you see here in that area, almost no entropic contribution, so enthalpically driven, no problem with solubility. So such information on how strong the enthalpy and entropy on the interaction is can also help to identify earlier on problematic compounds with respect to solubility, because compounds that are insoluble become a bit more challenging further down. Now we want also to look at the transition state. I showed you before with the airing analysis, you can also look at the transition state since we measure in real time. I pick here now 3 compounds because they all have a different transition state analysis. Basically, their profile is different. The first one, acetazolamide, and you see this here. So the first stage is the component separated, so analyte and target separated. Then the part here in the middle, that's the transition state, so when sort of a semi-complex is formed. And the third step here is then the final complex of analyte and target. You see here now in this graphic that the transition state energies in enthalpy and entropy are more or less similar. So going from the free compound to the transition state is controlled basically by both energies. However, if you go the other way around, so if you go from the complex to the transition state, then the enthalpic barrier is mostly relevant for that stage actually. Very differently, celecoxib, not surprising from the data that you saw before, is when you go from the complex to the transition state, so backwards basically, mostly entropically blocked. So the entropic component here is decisive. Whereas if you go from the free compound and the free protein to the transition state, both energy plays in. And the last example, the U104 is a compound that's solely driven by enthalpy, both in the transition state as well as in the overall reaction scheme. So no matter whether you go from the free compound or the complex into the transition state, the enthalpy is decisive, whereas the enthalpy doesn't play any role at all. Again, selectivity, interesting part. Now we want to understand whether binding to the 2 proteins shows also any difference, and actually it does. You see here encircled the compounds binding to Ca2, and in the second circle here to Ca12. You see that binding to Ca2 in the transition state energies is almost exclusively located here in the 3rd quadrant, whereas for the other ones, it's located in the 4th quadrant. So there's already a difference in the way the energies play into the activation energy. An interesting example, as a kind of picking that out, for instance, you see a celecoxib. You remember, entropically driven compound. The entropic contribution is decisive for this compound. However, there's a difference between binding to Ca2 and Ca12. So in Ca2, we land here in this third quadrant, and Ca12 in the fourth quadrant. So the impact is obviously a different one. There's a question now, why might that be the case? And actually such a finding could point towards the direction of making a structural analysis. In case of the carbonic anhydrases, if you look at the crystal structures available, and I picked here acetosolamide because there's the highest abundance of data for that compound, and you look now at carbonic anhydrase 2 specifically, you have this picture of the binding site. Here, the acetosolamide, the sulfonamide is complexed with the zinc ion that you see here in the center, complexed again also then by histidine. So that's the actual binding site. That's the same for all of the carbonic anhydrases. There are very small differences between them. The differences actually do not occur here at the central binding moiety, so the zinc ion, but around it. And a specific difference is highlighted here in red. This is position 131. In carbonic anhydrase 2, that's a phenylalanine. In carbonic anhydrase 12, that's a normal alanine. So you have a different bulkiness, you have a different hydrophobic element that comes into play, meaning the way the compound is binding to the protein has a different interaction space and wiggle room, in steric terms speaking, between the two proteins. And that can explain why there is also difference in the way the activation energies are composed. So out of entropy and enthalpy separately. With that, I come to the first conclusion. When we look only at the reaction energies, then we saw in the beginning that SPR and ITC yielded similar results for binding to carbonic anhydrase 2 for all the thermodynamic parameters, maybe delta G, delta H, or delta S. In addition, we were looking at the differences in enthalpy and entropy for the same compound between two proteins. And actually there we started to understand which components might actually, so whether it's enthalpy or entropy, might add to a selectivity driving mechanism. Third, the thermodynamic profiling that we did hinted also towards a compound, in this case celecoxib, having a relatively poor entropy-driven profile. And this can also already be a hint towards a problematic compound for further developability. When we looked at the transition state, we saw there that the transition state analysis revealed differences in the contribution of enthalpy and entropy to the overall activation energy of the compounds we tested. You saw there the three examples, acetosolamide, celecoxib, and U104, and each compound had a different influence, or like the activation energies of these complexes had different influences for each compound, meaning you can start to understand why some compounds might actually have that and that binding mode, because some are more enthalpically, some are more entropically driven, also in the transition state. And finally, differences in the activation energies may actually also correlate with structural differences in the binding mode. So such an example as we have here, when you were to do first the SPR experiment and got a hint, hey, there might be a difference, could now trigger the analysis of the crystal structures, or of the actual structural basis of the interaction, and give a better understanding, hey, there might be something different than between all of them. If you would just have looked at the KD alone, you actually wouldn't really realize that, and you wouldn't really care. Finally, on an experimental level in total, this example here showed you that with an SPR assay and a fairly simple SPR assay, you could determine thermodynamic constants, activation energies, so transition state analysis, as well as the kinetic constants within a single experiment in less than 20 hours. And this actually is then the fast track to thermodynamics, and why SPR is offering that. In case of our instrument specifically, they have a high degree of parallelization and multiplexing, meaning you have multiple channels and multiple spots, meaning you can immobilize multiple proteins, simultaneously allowing the measurement of different conditions and proteins. So you can measure 8 compounds at a time against 3 to 8 different proteins. If you were to do this in ITC, the gold standard technology, you would need to do everything one by one. That obviously will take you quite a lot of time. Typically, an ITC measurement is about an hour to up to 2 hours long, as you can expect to maximally measure between 8 and 10 compounds or interactions actually per day. You saw in our case, it was 8 compounds against 3 proteins measured in 18 hours, so in less than a day. Another point is sample consumption. Since you mobilize the proteins on the sensor surface, and in this case, they were also very stable, you do this only once, do the complete assay, and you save eventually also in sample. In an ITC experiment, you have for each measurement your own well, basically, that you need to use up. Automation, especially for those in the more industrial environment, is a critical point. If you want to speed up your process, you will at some point end up in an automation solution, and our instruments are ready to use. So you can basically run this also in an unattended way. Since these experiments tend to be longer than classical kinetic assays, since you measure them multiple times, obviously, at different temperatures, it's helpful if you can run the experiment in an automated fashion, so in a longer unattended way. More importantly, actually, for the fast track is the fact that you do one experiment, but you get multiple results, actually 2. So you do get the thermodynamic and transition state as one package, as well as the kinetic values directly out of it. So with just a small tweak, basically, to the experiment, you directly get a lot more information. From a biological point of view, this is also important because we're moving not only from an in vitro situation being 25 degrees, to a more in vivo relevant situation being 35, 37 degrees. Patients tend not to be at 25 degrees, or at least not those that we like to treat. So it can be helpful to analyze anyway the interaction at a higher temperature to already get an understanding how the binding might be. It can be that your off rate becomes so fast at 37 degrees that the compound might not actually be a good choice anymore to proceed in a further development stage. And finally, this goes specifically into the transition state analysis. Such an experiment allows you to get additional insights which you otherwise wouldn't get without doing complex structural elucidation studies, so NMR or crystallographic X-ray experiments. So basically, with relatively little effort, you get hints that there might be differences between compounds binding to a protein or antibodies binding to a protein, nanobodies binding to another protein, that can already help you early on. So when you have also a higher amount of compounds early on, start to decide, hey, this is something that I need to look at, or actually I don't really see a difference, so might not be that relevant. With that, I have come to the end of my presentation. I'm thanking you for your attention and to this matter, and especially to this very interesting topic. Before I conclude, I would also like to thank Dr. Satoshi Oshiro from Bruker, Japan, who has been conducting some of the experiments that you saw today, as well as to Dr. Martin Kleinschmidt from the Fraunhofer Institute in Halle, who has been conducting the ITC experiments that you saw in this presentation. And with that, I finally conclude. Thank you for your attention, and I'm now open to questions from your side.
Thank you very much, Cyrill, for this insightful talk. As he said, the floor is now open for questions, so please feel free to use any Q&A function or chat, or also raise your hand to ask your questions directly. Maybe you could also comment on the 64 you introduced in the beginning. The data was on the 32 Pro. How does the 64 compare to this? Does it have any different specifics for thermodynamics or in general?
Yes, actually, there are additional benefits coming with the 64. To start simply, the 64 has an 8x8 manifold, which means you can immobilize up to 8 proteins simultaneously. So you immobilize typically in vertical. You see here you have 8 channels, so you can immobilize 8 proteins. You rotate them to horizontal and inject your analyte as you would do on a Pro series or another SPR instrument as well in a multi-injection cycle kinetics fashion. So first of all, you already can get more interactions out of the same experiment. That's point one. Point two, the 64 has additionally the benefit that it can go in temperature lower. So the analysis temperature range from the 64 ranges from 5 degrees to 40 degrees, whereas the one from the Pro series typically goes maximally to 10 degrees, normally more 15 degrees. It depends a bit on the environment that you have the instrument in. So you can access also lower temperatures a bit better, which in certain cases might be necessary because you have problems with the protein instability and so on. And finally, the third element, and that goes again into the design of the manifold and the microfluidic design overall, you have on the instrument, let me quickly go back to the instrument themselves. Here on this side is the buffer panel. And the buffer panel allows not only to run one buffer across the whole surface, but it actually allows also to run up to 8 different buffers simultaneously. So you have per channel a different buffer condition. So in case you're looking at a thermodynamic interaction that might also be caused or like occurs in reality under the influence of different buffer components such as cofactors or some other buffer composition element themselves, so salt concentrations, for instance, the choice of the buffer element, so PBS versus HBS, or the pH in itself, you can measure that all simultaneously. So G64 adds then additional benefits when it comes to more multiplexing SPRs experiments, so you can do more at the same time. And this is important, especially when you do it like earlier on, so with a higher amount of compounds. It has a very good auto sampler solution, meaning you can combine it with a robot and can replace 2 plate positions at the same time. So you can run that instrument easily for days, basically, unattended, and get then the type of information that on the Pro would require a bit more manual replacement of plates at some point.
Thank you. And if we consider the sample preparations for these types of assays, so usually, as far as I understood, we covalently immobilize the proteins, but this could limit the movement of the protein. So should we also consider capture-based approaches for thermodynamic assays?
Yes, generally, in this case, we did amine coupling because the protein is very well known in that type of immobilization technique. But for others, it might be better to go with a capture-based approach. If you go for a pseudo-covalent capture-based approach, meaning biotin-streptavidin interaction, as an example, or SPITAG is another possibility, there's typically not so much to consider. The assay works pretty much identical as for an amine coupling. If you go for other capture-based approaches, such as FC capture or HISTAG capture, there actually you have to take a few things into consideration. You're heating up, so that does not only affect the interaction between the compound and your protein, it also affects the interaction between the mobilized protein and the capture protein, because that's also an interaction in that sense, non-covalent one. So that means the affinity goes down as you increase the temperature. In certain cases, that can become very problematic. So in case you use a classical mono anti-A sensor surface or a HISTAG capture sensor surface, your affinity will drop quite significantly by increasing the temperature, which could then cause a problem that you basically lose your protein too fast from the sensor surface. For that reason, we also have a different HISTAG capture sensor surface, a Trisentier, which has a higher, so like 1,000-fold higher affinity to a HISTAG than a normal mono NTA surface. But in general, if you do a capture-based approach, you have to make sure that your protein doesn't basically bleed away during the experiment simply because you increase the temperature. So you should check that up front before you do then a full kinetic assay.
If you're wondering about your specific situations or your specific proteins and whether they would be suited and which approach to use best, you can also, of course, reach out to us. Maybe we can go back to the last slide, and please feel free to reach out to Cyrill directly or to our general info email address. We're always happy to support or to organize a demo of our technologies using your own samples so we can see whether our technologies would work in your case. Now we are moving from the sample preparation to the data analysis. And you mentioned in the beginning that we need a linear change in the affinity or in the weight constants. What can we do if that is not the case? Is there still a way of analyzing the data?
Yes, there is. In case, and that can happen fairly easily because proteins do what they like to do once in a while. It can happen that the behavior or the change in the association dissociation rate constant is not linearly behaving to the temperature, but actually non-linearly. You see here one example, so you need to move to a non-linear fit. The degree of complexity obviously increases pretty quickly. So this is kind of the easiest additional case where it becomes a simply shaped curve. So it's just an additional term that you need to add to the equation. So a square term. Then this is doable. This is now one of the solutions for that specific case. What you need to do in addition, you need to measure more temperatures, because it can happen fairly easily that you oversee something. And if you basically measure here only every second point, then you might not really be able to get a very good fit eventually. So typically, if you have such a situation, it's recommended that you measure then not only like every 5 degrees centigrade increment, but with like 2 or 3 degrees increment.
Okay, I'm afraid we've run out of time for today's episode. I hope that we could give you a good overview of how you could do a thermodynamic profiling with SPR. And I thank you very much for your participation and the questions. And thank you again, Cyrill, for the talk and answering all the questions. And yeah, I hope to see many of you in upcoming episodes of this webinar series. You can find recordings of all our previous episodes on our YouTube channel, and the upcoming episodes will also be posted on our social media channels and can also be found on our website. So please stay tuned for upcoming webinars, and I wish you a very nice rest of your day. Goodbye.